So what's the focus today? So it's to give some insights about the the techniques involved for the generation of a semigroup um, for the heat equation with Dirichlet boundary conditions. And so to that we need an estimate of R lambda A. We need this estimate to apply the Heil-Yoshida theorem. And so we used the fact, so this relates, of course, to the study of the equation minus Laplacian u plus lambda u equals f and for f in LP. Okay, so we have the following theorem. So I took it from the book of Brazis about functional analysis, PDE, and stuff. This is a Springer 2010. So the theorem reads as follows. I can give you the page too. It's and so the theorem is referred as Agmon-Douglas-Nuremberg. So we suppose that omega is of class C2. So I recall that it means that you can write the boundary with a C2 function. And bound it. Okay, and now you define let's 1 less than p less than infinity. So then for all f in LP, there exists a unit Q in so it belongs to the Sobolev space. So you can you go to the up to the second derivative in yeah, so up to the second derivatives, and they are in LP. So all the functions and their derivative up to 2 are in LP, and this is Dirichlet. So it's it's the subspace so it's the closure of the regular functions that vanishes at the boundary in this norm. Okay, in this norm W2P. So this is the problem of Dirichlet. Okay, so basically the functions vanish at the border, at the boundary. And there exists a unique solution of what? Of my problem of you can write here, and you can write it for all positive lambda. Okay, so in basis there's no lambda here, but it's true for so let's lambda positive, you have that. All right, is if the boundary is more regular, and if f is if more regular, you can improve the regularity. And you have also the estimate. You have also the estimate, which is interesting for us, that the norm here is less than a constant times okay, so we did that actually. We proved the result for P equal 2. But okay, so the case when P is not 2 is much more difficult. So the aim of this lecture, of our discussion today, is to get some insights about the techniques involved in these results. So and to start, so I mentioned here these 3 names. So we can first have a look at 2 papers from those authors where a complete study of this problem is carried out. So this is one of the big contributions to the technical question of the estimates for elliptic operators in both LP setting and which we call a shoulder setting, which is the spaces C, continuous spaces C0 alpha, C1 alpha, etc. And I just want to go here through the so it's 100 pages, so we are not going through deal with that today, but we'll consider some ideas. So these are preliminary remarks, and then this is the outline of their paper. So, here you can see appear Poisson kernels, potential theory, general representation formula. So then Schroeder estimates. So we are going around these things today. Schroeder estimates, we are not considering that, but I will give you references. And here you can see LP estimates, right? So yeah. So there is this article, and there is another one, which is the part 2 that I'm not showing you, but which is also on the same idea. So you have the same title, but with a 2, and it came up a few years later. All right. So yeah, so today it's an invitation for you to look up at some of the references that deal with the LP setting. And so let me write here some important references for this lecture. So first of all, I already say that there's a book of Brazis. It's in Springer 2010, and I can give you the exact title. Yeah, it's a functional analysis, suburb of spaces, Harmonic differential equation. So there's a lot of comments in this book, and for example, the theorem that we started with is from there. This theorem, it's not proved in this book. In this book, you will find the complete case for the L2 setting, and a lot of results about suburb of spaces. But it gives you an important number of references. It's a very useful book for graduate students and beyond, but it gives you a lot of references. Okay, from there you have, of course, the paper that we just went through. So it's Agmon, it's a Nuremberg. It's 1959. So this is an important references for that. Okay, and next, of course, people from then have worked on that. So a very standard reference for LP spaces and also the Scholler setting is the book of Gilbert Schrödinger. So Gilbert Schrödinger. So this is an article. This is not a book. It's Springer, and it's specifically on elliptic partial differential equations. So it's called elliptic partial differential equations. It's 2001, right? Okay, you have also the book of Evans. This is also Springer. Also, it's partial differential equations. It's published by AMS, which is the American Mathematical Society. And it's also 2010. I can provide you some pages from it that specifically deals with the topic of today. And lastly, I like also the book of Just. I already gave you this this reference. And so it's also called partial differential equations. It's Springer, and you have an edition in 2013. All right, so that being said, now let's do some specific computations. So as I said, the idea is to dig into this problem. I write it with the minus, but that's not a big deal. But one one of the techniques to obtain results uh, so we start with this equation, and even more with this equation. So this is the Poisson equation, and this is the Laplace equation. So those are French guys. So yeah. And so to start with, I propose you the following exercise. Compute the log of here. So x is in R2, x is non-zero, and here this is the usual norm, so it's so compute the Laplacian of this thing. Okay, so try to do that. So let's compute this term here. Okay, so we want to compute the Laplacian of the norm of x. So it's x1 square plus x2 square and the square root of that. I want to compute this. So let's start with the first order derivative here of my log is, so I derivate the logarithm, so it's 1 divided by yeah, I put this one in front. So here I got that times 2 x1. So this cancels and I get x1 okay. All right, so but I want the second order derivative, so I just derive again, and I obtain, so the derivative of x1 is 1, so I obtain x minus x1 times 2. So this is x1 square plus x2 square. So just 2x1. divided by this quantity square, which gives that. So finally, I get what? I get 1 divided by the norm of x square minus 2 x1 square divided by x4. Okay, now, so if I do the sum, let's call it u. Well, so we get 2 divided by the norm of x square minus 2 x square divided by x to the 4, and this is 0. Okay. So I hope you were able to do the computations. So this means what? This means that so this so log of x is solution of so it's called harmonic functions. The functions that such that Laplacian u equals 0 are called harmonic functions. All right, so let's be more general, and let's assume that now I work with n greater than 3. And so I look for functions such that Laplacian u equals 0, right? And I would like to find a function such that u of x equals some phi of the norm of x. So where here phi is a function defined from R to R, and here x is the sum from I equals 1 to n of xi square, and so is the usual Euclidean norm in Rn. And so if I look at, so I want that Laplacian u equals 0. So this means that the Laplacian of phi of x equals 0. So exercise. Compute the Laplacian of phi of x for so x in Rn, and we'll assume that x is non-zero again, and phi from R to R. Yeah, can you do these computations and find look for a nice expression? And this you can call it R, okay, if you want. All right, so let's do this computation. So so now we write u of x equals phi of x. And okay, so let's compute the derivative of order 1 with respect to xi. So phi is a function from R to R. So I will get phi prime at here times 1 divided by 2. Let's do everything. Here I get minus 1 divided by 2 times 2xi. This cancels. So it's phi prime x. All right, so everybody agrees with that? Okay, so let's do it again. So if I want to take the second derivative, what do I get? So it's a product of derivatives. So I'll get phi second of x times, again, this term. So finally, I will get so this is, I derive this term times this one, I get that, plus phi prime of x times, and then I have to derive this one. So it will be so I can write it if you want as that. So this will be it will be x. So I take the derivative and I multiply by this one minus xi, and if I derive this one, I will get again I get this term again. So it's square and 1 divided by x, and here x squared. All right, now I need to do the sum over all that. So Laplacian of u x will be the sum from I to 1 of and so I get here, so that do this term so it's all right. So obtain that. When I sum up everything, I got that. And here, so this term doesn't depend on I. So when I sum up from I equals 1 to n, I will get n times. And here, when I sum up this cancel, so finally, what I get is that. Oh. Right? Yeah. So this is are you okay with that? So next, so let's so we look for a function phi which satisfies f second of r plus n minus 1 divided by r phi prime of r equals 0. Yeah, so all right, so if I put phi prime and phi second on the same side, okay, I can get that phi second r divided by phi prime of r equals 1 minus n divided by r. So, but I know indefinite integral of that, it's the log. So let's assume that f prime is positive. So I will get log of phi prime here equals 1 minus n log r plus some constant, right? So I get phi primes if I take the exponential phi prime equals r 1 minus n times a constant. All right. And okay, and if I do it again, it means that's phi equals so constant c r 2 minus n divided by 2 minus n plus another constant. Okay, let's choose this equals 0. So all right, so what I get that again, what I get is that so if I choose phi of r was a constant times r 2 minus n is harmonic. Because the Laplacian of u equals 0.